In the momentum transport section in the BSL, we are now in the chapter 6. In chapter 6, cover the interface transport in the isothermal system. In the basic section, subsections, the definition of the friction factor and friction factor for flow in the tubes and friction factors for flow around the spheres and friction factors for packed bed column. If you remember in chapter 3 and 4, we just go over some problems. These problems had some laminar flow problems, and we formulated them and we solved them, and we show in the actually for in summary to remember in chapter 3 we just show uh, the method and how to use the tables in appendix B and how to apply the conservation laws on the problem solutions. We start with problem solution with the conservation of the conservation of mass. Then we go over the conservation of the equation of motion. So then we just go in the chapter 3. They try to find in the problem velocity distribution dependent on the one variable. In chapter 4, we expand our discussion. Then we try to find the velocity distribution for depending on the two variables. The one is the spatial variable, either or x or y or z, and plus c, and we see the solution, mathematical solution methods of this kind of problems. Now we are in here chapter 6. Actually, if we know from the main engineering flow problems fall in the one or two broad categories. One is the flow in the channel, and the second one is the flow around some submerged objects. So the example of channel flow is the pumping of the oil through the pipe, or the second example, the flow around the submerged object or motion of the air around the airplane wing, or so another example we can give. In the channel flow, the main object is usually to get the relationship between the volume rate of the flow and the pressure drop or the elevation change. In problems involving the flow around submerged objects, the desired information is generally the relationship between the velocity of the approaching fluid and the drag force on the object. So these two things. For many systems, the velocity and the pressure profiles cannot be easily calculated, particularly if the flow is turbulent or the geometry is complicated. One such system is the flow through the packed bed column. In chemical engineering especially, we have this kind of reactors. They're packed with some catalyzed. We call it packed bed column or absorption columns or so on. Another is the flow in a tube in the shape of the coil. So for such system, we can take carefully the chosen experimental data and then construct the correlation of dimensions variables that can be used to estimate the flow behavior of the geometrically similar system. So in here, we are going to just define the friction factor. How can we evaluate this friction factor by some experimental correlation, so on. So what is the definition of the friction factor? We can consider for the fluid density, constant density, the fluid flow in the straight channel of the uniform cross section. The first type of system. The second type of system, the fluid flows around some submerged object that has an axis of symmetry or two plane of symmetry parallel the direction of the approaching fluid. So based on these two systems, there will be two forces. There will be force actually. We can call this force between the fluid and the surface exerted by the fluid on the solid surface. If you consider it as a solid, then it is convenient to split these forces in two parts. And we can call the first part as a Fs. This is the representation of the force that would be exerted by the fluid even if it were stationary. And the second one, the the force is the Fk, the additional force associated with the motion of the fluid. So there are two kinds of force. The first kind of force because of the fluid, even if it is in the stationary. Second kind of force is the because of the motion of the fluid. So in here, the Fk points the same direction as the average velocity in the channel, and in the system of type B, Fk points the same direction as the approaching velocity v infinity. So from here, for the both system, we can formulate the magnitude of the force Fk proportional to characteristic area A and the characteristic kinetic energy K per unit volume. Then we can write Fk by this formula. This A and K is the characteristic area and K is the characteristic kinetic energy per unit volume. So what is F here? In equation to calculate our force because of the fluid motion, we have some small f here. This f here is called the friction factor. Is the proportionality constant f is friction factor here. Now, for any given flow system, F is not defined until A and K are specified. Let us now see what definitions are available for. To calculate F, first we need to define our system characteristic variables area A and K. The case of A, flow in the channel. If you go flow in the channel after some evaluation, some mathematical evaluation, we get some what is Fk between two last two equations that gives these two equations there as a result give that. So we can calculate for the flow in the channel the friction factor by this formula or either if you know the friction factor we can calculate the pressure drop through the any channel. Let's say we have uh, if we have a channel like this and the flow is going here in this direction, so on. And if we know the F friction factor, we can calculate our pressure drop. Or either for the specific systems, we can get the friction factor by some experimental setup. So we define our system, we know the D, we know the L, then we can calculate the pressure drop and everything, average velocity, so on. Then we can get to our friction factor based on this experimental data. In here, these represent 2r is the tube diameter. Actually, these equations 6.14 show how to calculate F from the experimental data. The quantity F is sometimes called the fanning friction factor for the flow in the channel. In the second case, the flow around the submerged object, similar to the first one in the flow in the channel, we can obtain the friction factor by this relation. So this expression can be used to obtain F from the experimental velocity data. So when we set up some experiments and when we calculate the differences between these things, then we can find our friction factor. So the friction factor used in this equation here and in here sometimes called the drag coefficient and given the symbol CD. So we have seen the drag coefficient for submerged object and friction factor for channel and are defined in the same general way. In here, the book define the friction factor for in the same way, same symbol for the flow in the channel and flow in the submerged objects. But the first one is called the friction factor or just fanning friction factor. Second one is the friction around the flow is around going to any object. It's called the drag coefficients. So okay, we define what is friction factor and what is the how it's changed when the systems are changed, and we have two systems flowing channel flowing around some object. So we define the relationship. How can we calculate the frictions factors in base? How can we set up some experimental data to calculate the friction factor? So the friction factor for flow in the tube, I actually in here uh, based on these things, the obtained result, the friction factor is dependent on the Reynolds number, L over D, and the T, which means the time average. After we get the time average, we become the result of the F is now dependent on the Reynolds on NL and over D. When the time average is performed over the interval long enough to include any long time turbulent disturbance, the measured friction factor then depends on the Reynolds number and the length to the diameter ratio. After the integration, time average become when the time average is performed over the interval long enough. So then this other case, the velocity distribution is if the fluid developed in the transportation of the fluid, the entrance length is the usually a small fraction of the total, then this equation, this relation can be reduced this form, finding what we get, the friction factors only depend on the Reynolds number. So then the friction factor can be evaluated by experimentally fully developed flow at inlet and outlets basically. So we can find the relationship between the Reynolds number and the friction factor, and we can define our system friction factors based on our Reynolds number. So this section talks about that. Now basically, if you know our friction factor, if we can define our friction factor based on the system, we can calculate the pressure drop from this equation actually. So what is the definition of the Reynolds numbers? Actually, this is the definition of the Reynolds numbers here. So some examples here. If we continue uh, in section 6.3, the friction factor for flow around the sphere. Um, uh, if we go and again after some discussion for the time averaged over the turbulent fluctuation, we can get the simplification of the friction factor dependence on the Reynolds number. So this is the differences between the flow in the tubes and flow around the subsphere. We can find discussing here and so on. So if we continue from here, okay, this is the topic of the 6.4 friction factors for packed columns. So we are going to reach the final the equation, argument equation, and we are going to obtain here the insight of how can we get the argument equation from the definition. We know from the friction factor from the above discussion, we can write here. Actually there have been two main approaches for developing friction factor expression for the packed column. The one is the as visualizes the bundle of tangled in the tubes in weird cross section, the collection of these bundles inside of your system. And the theory is then developed by applying the previous result for single straight tubes to collection of all these tubes. For the second method, the packed column is regarded as a collection of the submerged objects, and the pressure drop is obtained by the summing up this resistance of the submerged particles. But the books in here that use the first approach, was the tube bundle theories have been somewhat successful. That's why it's used in here, the bundle uh, model. So from the definition of the friction factor, starting from this equation, friction factors can be defined like this. Then the pressure drop through the representative tube in the tube bundle models gives uh, that uh, discussion. We call it F tube here. Then finally, the friction factor uh, can be calculated from this relation. In here is the F tube. We know the relation F tube, and when this is finally, we can get in the pack bed what is the friction factor is going to be, that one. Now we can, based on the F2 definition of the F2 for a specific system, we can find our friction factor. For example, the first case A, for laminar flow in tubes, F2 can be defined 16 point Reynolds number. Then if we write this in here by the open form of the Reynolds, we can obtain that modified expression for the friction factor calculation in the laminar flow in tubes. And we can write the pressure drop by inserting in the equation of the 6.41. We can write the pressure drop by this formula. For the second case, for the highly turbulent flow, we can take the F tube 7/12, and we can insert the into the equation 6.47. We can get that result, and we can take this F friction factor calculation and substitute into the 6.41. We can calculate the pressure drop by this formula. But for the transition region, we may sum this A and B two effects. If we sum these two effects for the pressure drop, this relation from here and this effect from here, we obtain that result for the pressure drop calculation. This equation here, um, uh, we can rearrange this equation like this, and this equation is called well-known equation is Argon equations, which is shown in the figure 6.4 along with the so on, so experimental relation. So the Argon equation, but one made that have been proposed was described in Peck column, for example, other form of Argon equation. So this is the how this Argon equation comes from. The Argon equation comes from. So what did we do in this section? We just uh, define the Peck column based on the theory of the what was the theory? Theory was like a collection of the tubes bundles, and then we start discussion the friction factor in the channel. Then we define a new friction factor F tube. Then we just define our friction factor based on the dependence of the F tube. Then we calculated F2 based on the different cases. First one is the laminar flow in the tubes, and second one was the high turbulence flow. They've calculated the pressure drops for these cases. For the case 3, we calculated the transition region, the collection of these two A and B, and we obtained the pressure drop in the transition region by this formula. And we call this formula and arrange this formula, and we obtain the Argon equation finally from this section. So this is the important points I just want to touch in chapter 6. Now after this video, in the next video, I'm gonna go uh, jump in the energy transport section. Later, maybe in later videos, I'm gonna come back in the chapter 7, some macroscopic balances in isothermal flow system. But now in the next video, we are gonna go and jump in the energy transport, and we are gonna start with the chapter 9. So see you in the next video.